All right, so we have to define inverse cosine fairly similar way to the way we did inverse sine. Specifically, the cosine function is not one-to-one either. Okay? But again, we're going to take the cosine curve, and what we're going to do is we're going to restrict the domain so that we capture as much behavior as possible without duplicating any y values. So since we start at a maximum, at the angle equals 0, we just go from the maximum to the minimum. So we go from this maximum point of the cosine curve, 0, 1, down to the minimum, pi, -1, and that's our restricted cosine function. It now passes the horizontal line test because it's only going from its max to its min, and then it stops. So we can invert that, and let's ask what's going to be the domain and range of the arc cosine function. Okay, and remember, sometimes I might write out arc cos rather than cos with a little exponent on it. Well, the domain of the arc cosine function will be the range of the function it's inverting. Okay, and the function it's inverting goes from here to here. So what does it output? Everything between -1 and 1. So the domain of the inverse function is everything between -1 and 1. The range of the arc cosine function will be the domain of what it's inverting, and the domain of what I was inverting started at 0 and ended at pi, so that's going to be the range. Okay, so just like arc sine had a range from -π/2 to +π/2, because that's where I could restrict sine to be 1-to-1. Arc cosine has a range from 0 to pi, because that's where I can restrict cosine to be 1-to-1. Okay, so let's try to find the value of the arc cosine of 1/2. We're going to do this pretty similar to how we did the previous video. Arc cosine of 1/2 means an angle whose cosine is 1/2. And if I draw, I'll erase this in a minute because there is bookwork coming, but if here's the unit circle, and I say I want an angle whose cosine is 1/2, that means I want the x-coordinate on the circle to be 1/2. So if I draw the line x equals 1/2, it's right here. And again, there's 2 points on the circle, but that actually represents infinitely many angles because you can wrap around however many times you want. But specifically, we're looking in an angle between 0 and pi. That's quadrant 1 and quadrant 2. How many angles in quadrant 1 and 2 intersect this line x equals 1/2? Just this one right here, and we measure off that angle. Okay. You can find that angle now by checking a chart of known values, or maybe you just kind of remember it. Okay. So what's an angle whose cosine is 1/2? In between 0 and pi. The angle has to be in quadrant 1 or 2. Well, we only have one such value in between 0 and pi, and it's at pi/3. Okay, so there is the point of intersection. When the angle is pi/3, the cosine is 1/2, so that is the arc cosine of 1/2. It's the only angle in our restricted interval whose cosine is 1/2. Okay, and again, there are other angles whose cosine is 1/2, but there's only one angle in between 0 and pi whose cosine is 1/2. So specifically, arc sine is only going to produce angles in quadrant 4 and 1, from -π/2 to +π/2. Okay. Arc sine is dealing with a y-coordinate, and I get all the y-coordinates in quadrants 1 and 4. Arc cosine is dealing with an x-coordinate, and I get all the possible x-coordinates in quadrants 1 and 2. So arc sine produces angles in quadrants 1 and 4, while arc cosine produces angles in quadrants 1 and 2. Okay, so there we have it. Arc cosine of 1/2 is pi/3, as already stated. So let's do another example. Find the exact value of the arc cosine of -√3/2. So pause the video and see if you can find it. And remember, you're specifically looking for an angle in between 0 and pi whose cosine is -√3/2. So pause here. All right, so in between 0 and pi, the only angle whose cosine is -√3/2 is right there at 5 pi/6. There's the point of intersection. the angle is 5 pi over 6, the cosine is negative root 3 over 2, and while there are plenty of other points whose cosine is negative root 3 over 2, this is the only one in our restricted domain. So the arc cosine of negative root 3 over 2 is 5 pi over 6. Okay, we've got arc sine, we've got arc cosine. We can also do inverse tangent or arc tangent. And again, just to let you know, it's sometimes written as tan with an exponent of -1. It's sometimes written like this. The arc notation, arc sine, arc cosine, arc tangent, is a little older. It's a little old-fashioned because it used to take more effort to typeset exponents in books, so they would just use letters, arc tangent, as inverse tangent. But it's still pretty commonly used. Okay, it's not like this is super antiquated and no one ever does it anymore. Plenty of people write out arc sine or arc tangent. Okay, so think of the normal tangent function. Its graph, remember, looked like this. It spectacularly fails the horizontal line test, unless I restrict the domain so that I'm only looking at one branch, and the standard branch was between negative pi over 2 to positive pi over 2. So that's how we restrict the domain on our normal tangent function. So on the figure we see in the pink, they've cut off the domain to go between negative pi over 2 and pi over 2, so that the pink tangent curve is just one branch of it, no duplication. Then it is one-to-one, and then you can invert it. Okay, so let's ask again, what's the domain and range of the arctangent function? So the domain of arctangent will be the range of the thing it's inverting. So what is the range of one full branch of the tangent function? So one full branch of the tangent function goes all the way between plus or minus infinity. It's got the negative vertical asymptote on the left and the positive vertical asymptote on the right. It fills everything in. So the domain of arctangent is all numbers, because the range of the tangent function on one branch is all numbers. In contrast, the range of arctangent will be the domain of the restricted tangent function, and we restricted the domain to just go from minus pi over 2 to positive pi over 2. So similar to arc sine, which only produces angles in quadrant 4 and 1, arctangent also only produces angles in quadrant 4 and quadrant 1. All right, so let's look at an example. Find exact values for each of the following: arctangent of 1 and arctangent of negative root 3 over 3. So again, you're looking for an angle whose tangent is 1, but specifically an angle either in quadrant 4 or in quadrant 1. So pause the video here and try to do both: an angle in quadrant 4 or 1 whose tangent is 1, or an angle in quadrants 4 or 1 whose tangent is negative root 3 over 3. Pause here. Okay, so continuing, we're looking for an angle whose tangent is 1, but specifically the angle is in quadrant 4 or quadrant 1. And for part B, similarly, we're looking for an angle whose tangent is negative root 3 over 3, but specifically an angle in between negative pi over 2 and positive pi over 2, aka quadrant 4 or quadrant 1. So if we look at the table of sort of reference values of tangent, okay, remember our standard values that we can compute trig functions for exactly are at pi over 2, 3, 4, and 6, plus or minus, and then rotated and shifted around the circle. So here are our standard values. And we find that at negative pi over 6, the tangent is minus root 3 over 3. So that's the arctangent of negative root 3 over 3. It's minus pi over 6. Similarly, okay, it didn't bother doing it. What's an angle whose tangent is 1? Pi over 4. Okay, so there we have it. We've learned the inverse sine, inverse cosine, inverse tangent functions. You might ask, are there inverse secant, inverse cosecant, and inverse cotangent functions? Yes, but pretty much no one ever uses them, okay? Like, seriously, you never see them in use. Arc sine, arc cosine, arc tangent, those come up a lot. The other ones are vastly less common, so we're really not going to focus on them. Okay, but come on back in the next video and we will start learning properties of these inverse trigonometric functions.